We're covering chapter 3, measures of central tendency. It's an important week for us. We're going to be building on these concepts each subsequent week. So let's start with our learning objectives. First, we're going to explain the importance of these 3 different kinds of measures of central tendency. By central tendency, we just mean typical or expected values. Second, we're going to calculate and interpret the mode, the median, and the mean. Those are our measures of central tendency. Third, identify the relative strengths and weaknesses of the 3 measures. They capture slightly different things. Sometimes they're really similar, but we'll also see some cases where there are trade-offs. 4, we're going to determine and explain the shape of different distributions. What's a measure of central tendency? These are numbers or observations that describe what's average or typical along a distribution. So you can think of this value as where the middle of a distribution lies. So all 3 measures are trying to get at this concept, but how we get there is slightly different depending on which measure we have in mind. Start with the mode. The mode is a category or score that's going to have the largest frequency in a distribution. So in chapter 2, we introduce frequency distributions, where we tabulate how many observations there are per category. The way to know that you're looking at the mode is the most common value. What comes up the most? You might also hear me talk about modal values. By that I mean a modal value is the most common value. We'll see some examples in a moment. The mode can be calculated for nominal, ordinal, as well as interval ratio variables. So we're going to see some examples of stata using the tabulate command for nominal variables as well as for ordinal variables. And it's less common to calculate the mode for interval ratio variables, but we're going to see an example of how to do that in stata using this command, the egen command. With nominal data, if we want the mode, all we're doing is looking for which of these categories has the most observations. So here I tabulated our variable we worked with last week of English speaking ability. And clearly, by far, the most common is this category. That's the mode. 2.3 million people who answered, yes, I speak English. In fact, I only speak English. These are monolingual English speakers, the most common. If you're looking at ordinal data, like educational attainment, here I'm tabulating the EDUC variable, which is educational attainment. And the categories range from no schooling all the way up to 5 or more years of college. So again, look for which category has the most observations. There it is, grade 12. So people who finished 12 years of school, the equivalent of a high school degree or a high school diploma, is the largest frequency here. That's the mode. How do we get the mode for continuous data? So here we're thinking of interval ratio. Well, it's less common, but there's a way to do that in stata. So think about year of immigration. Year of immigration, the variable in this data set from the American Community Survey is YRIMMIG. Year of immigration only applies to immigrants, and the earliest year of arrival is 1919 in this data set. So there are individuals who arrived as immigrants as early as 1919 in this data set. And it goes all the way to 2020. So there are the newest immigrants who came to the US in 2020. How are we going to do this? Well, look at my command here. I've got summarize. I want to summarize this continuous variable. You could tabulate year of immigration, but if you did that, you'd get this really long list of years. That's not very useful. So if you summarize year of immigration, you're going to summarize if the year of immigration is not 0. And that's our if statement. Very handy. It's going to help us be more specific with what we want the data output to tabulate or summarize. And we're interested in cases where this variable is not 0. Exclamation equal sign is another way of saying is not 0, right? So if year of immigration is not 0, that then means we're only looking at immigrants, because 0 is assigned to people who were born in the US. Why? Because they never immigrated. So they're assigned a value of 0. So we can see the mean here is 1988. The mean year for when immigrants arrived in the US is 1988, and we'll formally define the mean in a moment. For now, let's talk about how we're going to get the mode. I'm going to use this command, egen command. This is going to generate a new variable that I'm going to call YR_immig, year of immigration, underscore mode. I'm creating this name. I could have named it whatever I wanted. Set that equal to the mode, and that's going to be the way that we're going to calculate the mode for year of immigration. And again, don't forget the if statement, if the variable is not equal to 0. So again, this is a brand new command that you can use for all sorts of things, and we're going to use it here to create a new variable. We're going to calculate the mode as a statistic for that variable with our if statement. And lo and behold, when you do that, you calculate this new variable that you can summarize because it's continuous. Why is it continuous? Because the original variable of year of immigration is continuous. And now we have some really useful information here where the mode is the year 2000. There it is. Not very common, but just wanted to show you how to do that. Caution number 1 with binary variables. The modal and non-modal values might be very similar if you're working with dichotomous variables. In the ACS, the sex variable, if you tabulate it, it is a binary variable. It only has 2 categories, either male or female. But careful, because the modal value here of female is only barely the modal value, right? Male is a close second. But the correct answer here of what is the mode is female. Another caution, if you are calculating the mode, in this case, we're looking at the mode for age, you want to look on this histogram for the bar that is the tallest, and that's going to be this bar representing people who are in their 50s. So the tallest bar here is going to be people in their 50s, and that's one peak in the distribution with the mode. But if you look along the full spectrum of the distribution, this is one cluster. There is a second cluster earlier in the distribution among people who are approaching early 20s and in their early 20s. So you could talk about this as having 2 peaks. Another way of saying that is this is a bimodal distribution because there are nearly two modes, right? We've got this really tall peak here and another one here. And they're far apart because they're separated by these values that are relatively low. It's a bimodal distribution. So let's talk about the median now. In order to get the median, you line up scores from lowest to highest. So here's fictional data here. Professor Pedrosa's hours of sleep from 6.6 up to 9.2. And to get the median, you do need to line it up in order. So you can see each number is bigger than the last. And you look for the middle spot. Here it's 7.6. It's the middle score. This is different than the mode. The mode is the most common value. Here there isn't a most common value. Every value is different. That's where the median comes in handy. We can just look for the middle number. Instead, you can calculate median easily. So we're going to calculate median for prime working age adults, median income. So we're going to summarize this variable called income and wages, but only if it meets 3 conditions. First condition is income and wage has to be less than this value, and that value means that it is not applicable or not in the universe. So that's a top code. We want to exclude those cases. These are either people who are not in the workforce or too young to be working. Also want to only include people in their prime working age, so age 25 to 54. So age is more than 24 and less than 55. And finally, the third condition, want to make sure to set employment status to 1. Employment status is equal to 1. Comma DE. This is going to tell Stata that we don't just want to see the mean and a minimum and maximum value. We want to see all of this detail here that you see in this output. And DE stands for details. And that's what we get. We're going to get all of this detail. We still have the mean income and wages, about 46,000. The median is 35,400. What's handy about these details is we don't have to be limited just to the median, which is technically the 50th percentile. So the median is the 50th percentile. We can look at the 75th percentile, right? How much in this group of individuals from the ACS, the American Community Survey, who are prime working age adults and working, what's the 75th percentile? It's 60,000. That means if you're making $60,000 or more, you're earning more than 75% of the people in this survey. What about the top 1%? If you want to know the top 1%, you got to look at the 99th percentile, which is here. That's $296,000. Very useful information calculated across these 900,000 people. Now we're ready for a measure we'll be talking about the rest of the quarter, and that is the mean. The mean is also a measure of central tendency. We obtain the mean by adding up all the scores along a distribution and divided them by the total number of scores or observations that we see. It's also called the arithmetic average. Typically, we want to use this here with interval ratio variables. It is the best known and most widely used measure of central tendency. So let's take a look at some examples. So breaking down the equation, what is the mean? This is one way to talk about what the mean is about. So we've got y bar. Y bar is the mean. It's going to be equal to this numerator divided by the denominator. Here, the numerator is sigma y. What is sigma? Sigma is notation. That's asking us to add up, to sum all of the observations for y. Y is our variable of interest. So we're going to look at every single observation, look at the value for every observation, add it up, right? Because y is the actual values for each observation. And once you're done adding all of that up, you divide it by the total number of cases. So that's what that means. Let's look at an example. Let's say you had just 5 observations, 1, 3, 2, 5, and 7. What does this equation mean? Well, it means that you add up 1, 3, 2, 5, and 7. That's 18 divided by the total number of observations. This is simple enough to do because there's such a small number of observations. That's 5. 18 divided by 5 is 3.6. And we're not even mad at this equation because it's so handy. Of course, you can imagine this gets very unwieldy when you're dealing with thousands, hundreds of thousands, or millions of observations, which is why we're going to have Stata help us do the heavy lifting. You can do the mean in Excel as well. Here's an example. Let's say you have these 5 observations across rows 2 to 6. Then in here, the example is in column C, row 8. Inside of this cell, you type equals average, open parentheses, starting from cell C2 down to C6. That'll calculate your average. So the average across these 5 observations is 25. It's that simple in Excel. Stata can also, of course, calculate the mean. We saw an example earlier. Now let's take a closer look. We're still summarizing income and wage for the same group of people employed, prime working age. It's 900,000 people. And that'll give us the mean, 46,000. We saw this number a moment ago, right? You can also do a histogram. A histogram is a visual way of looking at that distribution for income and wage. And we're going to display it across 53 bins. So there are 53 bars here along the histogram. So again, hist here is an abbreviation for histogram for this variable, the same condition on the if statement. And then we add, comma, we want to look at the frequency because each of these bars is going to give us a frequency across 53 bins. And notice something, if we were to ask for the mode, we would look for the bar that's the tallest. And notice how the mode here is left of the mean, because that red dashed line is the mean of $46,000. So right away you can see, why is the mode to the left of the mean? Shouldn't they be close? Well, they would be, except that we have so many high income earners here pulling the average up. So these outliers, these high income wage earners, are pulling the average higher than it otherwise would be. So if you wanted to know what's a typical value for income, well, it depends. Do you want to know the mean? That's $46,000. But if you want to know the mode, here, just visually, we can see that the mode is going to be something smaller than $46,000. Let's get specific here. Let's say you wanted to know, what does middle class income look like? You could calculate the mode using the exact same method I showed you earlier. Turns out the mode is $30,000. So I've just zoomed in on the same graph we saw a moment ago, and now I've identified the mode in this red line, red solid line, that's the mode. You go to the median, and the median, what's the median? That is the 50th percentile. That is represented by this blue line. So the mode and the median are relatively close. They're about $5,000 apart, both of them under $40,000. Pretty different and much lower than the mean. The mean is all the way up here at $46,000, and it's getting pulled to the right because of the outsized influence of high income earners. So let's be mindful when we're talking about a typical value. What do we mean exactly? If we're having a conversation about what it means to be middle class, we should specify what we have in mind. Other kinds of conversations, of course, when talking about income, it might be that we're not interested in a typical value in terms of a mode or a median or a mean. We might instead be interested in what's a livable wage. It's a typical livable wage. We would need to revisit this question and see if we can use the data to answer this question, right? Of what is a livable wage? Is it something like double the mean or double the mode? Might it vary across places? This is another way to use data to help have more precise conversations. It's time for a reminder on continuous versus categorical data. Year married is continuous. Year is a number. It's a number that we can perform statistics on because we can add it, we can divide it, because of course it is a number, and we can think of a fraction of a year being, for example, it could be months or some subset of a year. So year married is continuous, but by contrast, marital status is categorical. Categorical. So these are categories that we're talking about. The ACS reports 6 different categories for marital status. The variable is named MARST. Each category has a label. An example of a label is married with spouse present, for example. And each label also has an underlying numeric value. We're going to look at an example on the next slide. If you ask Stata to summarize marital status, Stata will return a value of 3.58. But be careful, that's not very meaningful. There's no such thing as an average marital status here. The reason Stata calculates an average is because each of these categories have an underlying number associated with it. Let's take a close look at what I mean. So here, if you tabulate marital status, you'll see the distribution here. The mode is married with spouse no present, but that's also going to include people who've never been married. If you tabulate the exact same variable and specify comma space no label, that's going to show you the underlying numerical value underneath these labels. And you can see that married spouse present corresponds to a value of 1, and never married single corresponds to a value of 6. This is why Stata thinks that it can calculate a statistic for this variable, even though we know it's not meaningful. So be careful not to summarize categorical variables, even if they've got an underlying numerical value, because what you really want to do is tabulate these categorical values. What is the mean year that people got married, assuming that their marital status is not equal to 6, and 6 is single, and you're over age 14. What does this mean? We're interested only in people who have ever been married, so we're excluding the single people in the survey, and only if you're 15 or above. Okay, so the average year that you got married in this data set is 1984 across 1.8 million observations. The earliest year of marriage in this data set is 1928. The most recent is 2010. You can do a histogram of year married because it's a continuous variable. And again, histograms are very handy for continuous variables like income, age, year married, with the same if statement. We're only interested in people who are not single, who are 15 years or over. And this displays the frequency as bars. That's frequency across 53 bars or 53 bins. And the dashed line is the mean. That's 1984, the year that Prince drops an incredible album. This is one of the more important slides. You should be taking a close look here because we're going to revisit these issues again and again. The properties of the mean. The mean has some important properties we need to think about when we're looking at interval ratio levels of measurement. We're looking at variables that can be added and divided. You can take the mean if they're interval ratio. And when we take the mean, what we're capturing is the center of gravity along that distribution. And it's a handy measure because unlike the mode where we're looking for the most common value, and unlike the median where we're looking at the 50th percentile, right in the middle of that distribution, to calculate the mean, we saw in our equation, we're incorporating information across all of the values in our distribution, which makes it really handy and useful. So when we're calculating the mean, we need to know every single observation in a way that we don't for the mode or for the median. You can just look at the 50th percentile for the median or the most common value for the mode. For the mean, we are looking for the point along the distribution that perfectly balances all of the scores in a distribution. So it's a very sensitive measure, which makes it powerful. But because it's a sensitive measure, it does have a downside. And we already saw an example of this. It can be very sensitive to extremes. We saw this when we were looking at income data. High income earners can really throw off the mean. The mean can be pulled in the direction of extreme values. So that's a downside we need to keep in mind, and we'll come back to these issues for the rest of the quarter. We're now ready to talk about the shape of a distribution. We're going to look at some symmetrical distributions and what they mean. By symmetry or symmetrical, we just mean it looks like a bell curve, and we'll see an example in a moment. So this is an important shape because when we have a symmetrical distribution, we're in a situation where the mean is about equal to the median. That's not the only kind of distribution we could have. We could also be looking at a skewed distribution, either a negative or a positive skew. We'll define those in a moment with some examples. A negative skew is a case where the mean is less than the median. Positive skew means that your mean is larger than the median. But before we get there, let's talk about symmetrical distributions. Here's an example of a symmetrical distribution. This is a case where the mean, the median, and the mode are about the same, if not identical. There are just as many observations to the left of the middle of the distribution as there are to the right. With a positive skew, that's not true. Your mean is getting pulled to the right. This is very similar to our income example. And median and mode are going to be lower than the mean. A negative skew means that there are observations here at the tail end on the left pulling that mean down to be lower than the mean and then lower than the median or the mode. Here's an example of a negatively skewed distribution. It's ever so slightly negatively skewed because the median is 40 years old and the mean is 39 years old. So they're really close, but technically this is a negative skew, and I think it's easier to see if we plot it as a histogram, which we'll do in a moment. But before we do that, US population, let's look at the US population by citizenship status, because we're going to need to break down these age distributions by citizenship status. So we're going to tabulate citizen variable. Has 4 categories, including immigrants. Immigrants here are either naturalized citizens or people who are not a citizen. Those born in the US are coded as not applicable. Citizenship status means that you're coded as a 0 because you're a citizen by birthright. There's also a small number of observations of people who are born outside of the US, but they're born to parents who are US citizens, and by default, they themselves are also US citizens. So the US born, so these are people, we're going to summarize age for the US born, summarize age if your citizen variable is set to 0, and we're going to look at the details. Notice here, now we're getting a more clearly negatively skewed distribution where for the US born, median age is 40, mean age is 39. This is for the US born. And this histogram shows why it is skewed. Here we have the median at 40, which is greater than 39. It's not a symmetrical distribution. It actually also looks like it's bimodal, right? It's a bimodal and negatively skewed. There's a histogram of age if citizen is set to 0. So these are only US born people. We want to look at the frequencies across 53 bars or 53 bits. This is different than the immigrant age distribution, which is not negatively skewed, but instead is positively skewed. Why do we say that? Well, let's take a look. Let's summarize the same variable age, but this time only if the citizen variable is greater than 1. And that's going to include only immigrants, either naturalized immigrants, citizens, or non-citizens. Okay. And now here we see that the median is 43, which is smaller than the mean of 44. So immigrants skew the age distribution to be positive. You have median is smaller than the mean. And this looks close to symmetrical, but technically it is skewed positively because of the median and the mean. Here we've done a histogram for age, but only if your citizenship status is greater than 1. If you look at them side by side, now you can see the skew. On the US born, you have a lot of older people, including people past prime working age. On the right, you have immigrants who are heavily concentrated among prime working age and young people. So how do we decide which measure of central tendency is going to be right for us? We've got a lot of options. If you are working with nominal categories, look for the most typical value. That's going to be your mode. We have ordinal data with ranked order, categories with the ranked order. You can also look for the most typical value by using the mode, or look for the 50th percentile in a distribution. We have a lot more options if we have interval ratio data. First, look at the shape of your distribution. If it's symmetrical, then your mode, your median, and your mean are all going to be roughly the same, if not identical. So you can choose any one of those for a symmetrical distribution. Typically, we choose the mean. But if you have a skewed distribution, you want to be careful. The mean is not going to be very helpful. It might even be a little misleading. So we might instead calculate the mode and or the median, and that's going to give us a better sense of where we are in the distribution. So pay attention to what kind of variable you have, and if you're working with interval ratio data, whether or not your distribution is symmetrical or skewed. Vocabulary for today, we looked at measures of central tendency, mean, median, and mode. We talked about percentile, the 50th percentile being the median, but other percentiles as well. And then we ended by comparing symmetrical and skewed distributions, either negative skews or positive skews, by looking at the case of US born versus immigrants. See you next time.